Howdy everyone, I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I share all my lectures in data analytics, geostatistics, and machine learning. Now this week I've given my students an assignment to do variogram calculation, and we've discussed it in class. There are recorded lectures available to you on the YouTube channel right before this lecture that can help you out with the theory and concepts. There's even a discussion about the search parameters for variogram calculation. What I'll do right now is just walk you through how do you accomplish variogram calculation in Python. And so I have a well-documented, worked out workflow for you doing this with the synthetic data set that should really help out. So if you go to my GitHub account, I'm the Geostats guy on GitHub, and what you'll see is that I have a GeostatsPy. GeostatsPy is my package. Now you can download that from PyPy. Just do the pip install GeostatsPy and you'll go ahead and get that package locally. And if you go to my Python numerical demos, what you'll find is I have a whole bunch of demonstrations available to you on geostatistics. All the GeostatsPy _ workflows are all around using GeostatsPy package to do spatial data analytics and geostatistics. Okay, so if you keep going down here, what you should find is a variogram calculation one. Okay, that's going to be the one we're going to work with. So that's exactly what we have right here. So I've just loaded it locally. I'm going to run it locally and we can walk through it. So I'll just walk through it with you right now so that you can understand what's going on. So go ahead, if you open up, download and open up this workflow, what you'll find is I have a little bit of explanation about spatial continuity. I explain about the variogram. The variogram calculation is going to require us to identify pairs separated by lag vector h within the area or volume of interest. And we'll go ahead and calculate 1/2 the average square difference of those pairs. Okay, and I explain how that's related to the covariance function, and it can be related to the parallelogram, and specifically if the variance is equal to 1 with a standardized variable, the covariance function is equal to the parallelogram because the variance of the phenomenon goes to 1. And then I make some observations about variograms, and these are all available in the lecture notes, so I won't spend any time on this right now. All right, let's keep going. Let's go ahead and run some code, make some observations. I think this should be helpful. Now, first and foremost, I should restart and clear all the outputs so we're running this nice and fresh. Then we get to share the sense of adventure, or maybe just the feeling of terror, wondering whether or not the code's going to run, right? Kind of fun. So let's go ahead and first of all, we'll import GeostatsPy. GeostatsPy has a whole bunch of visualization and utilities that are implemented in Python from the original GeostLib, but also it has some wrappers where it takes the more complicated algorithms and just wraps them, not in a sophisticated manner. Really, all it does is just sends out a parameter file, runs the executable, reads the output back into your Python workflow. It's not great. I did that as a stopgap. But then what we have is the geostats are all of the GeostLib methods, geostatistical library methods from the original Deutsch and Journal package, or I should say Fortran code, as re-implemented in Python. And I'll say it's not really fully optimized. It was more kind of quickly done because my students needed it. I was doing it last spring, the weekends right before lectures where the students needed to do it in class. So I was working 7 days a week. It was nutty. Okay, so let's go ahead and load that up. Did you need the history? Probably not. Okay, so we went ahead and we imported that. Now we have GeostatsPy. We'll just need OS so we can set a current working directory, NumPy so we can work with ND arrays of data, and pandas for data frames, and matplotlib for doing some basic plotting. Okay, so we'll go ahead and import that. Now what we'll do is we'll set a working directory. Now I know more sophisticated individuals who are, like my collaborator on Datum would do things like use intake for proper feature engineering. What I'm doing here is I'm just setting a working directory where the data is and loading it in from a simple ASCII file, comma delimited. It's easy, but there's of course more sophisticated things we can do with data engineering. So don't get me wrong, we're just showing something very simple here. Set the working directory. You'll need to download the specific data file to work with. The data file is available here. There's a link right here in the workflow. On my GitHub account, you can just download it, put it into a working directory that you choose, set this equal to that working directory, and away you go. So you run that to set the working directory. Now when you run this command, it will go to that working directory and load sample underscore data CSV. Now if you open up the data file in TextPad or some other type of just simple viewer, you'll find out that it's just comma delimited, value, comma, all the way across the row. That's one sample, all the features, and then it just keeps going through all the samples. It's really simple. So let's go ahead and load it, make sure it works. We'll do a preview with the head command. So we've loaded the data from comma delimited using pandas. Remember, we imported pandas as PD. Read CSV will create a data frame. DF is now a data frame. Now we can go ahead and work with that data, do some data checks and so forth. Now we're not going to do very much here. Please take my word for it. When we do a typical project, 80%, 90% of the effort is data prep. So clearly I am making this simplified, truncating somehow this workflow to get straight to the point of variogram calculation. Now what we'll do next is we have, if you look at data, we have facies 1 and 0. 1 is sandstone, 0 is more of a shale. And so we'll separate it out. We want to calculate variograms by facies, but we'll also do variograms over all of the facies at once. So we've got both, and so we need to create two new data frames. One is going to be a sand data frame, one's going to be a shale data frame, and then we'll have the regular DF, which is going to be all of the facies all mixed together. And so we can go ahead and create a copy, and all we have to do is say, well, let's go ahead and export all samples for which DF, the data frame facies feature, is equal to 1 and equal to 0. We'll reset the index so that we don't have a discontinuous index. That can cause a problem with some of the operations we might do. Not a big deal for what we're doing here. Okay, so we go ahead and we create the new data frames. Now we just visualized SAM 1. You can see all the facies are all equal to 0 to 1 there, and so those are all sand. And we can go ahead and preview the shale, and if you look at that, they're all 0. So that it works. So we have two separate data frames by facies that we can work with. Now it's always a good idea to do summary statistics. I mentioned we're just doing a couple things for data checking, not too much here. So we can go ahead and look at the sand summary statistics. Something of interest, take a look at the min and the max for porosity. We'll be focused on porosity in this study. So about 8% to about 24% porosity for our sandstone here. Okay, so this all facies 1. Let's go look at the shale. You look at the shale, now we're talking about porosities going from about 5% to about 14%. Distributions are overlapping, but they're shifted lower for sure. We've got systematically lower porosity in the shale versus sandstone. Now, we're going to do variogram calculations here, and we're going to want to do a normal score transform. Now, there's a couple reasons for this. First of all, if the variograms are going to be used in simulation, like sequential Gaussian simulation, which is variogram based, those variograms should be of the normal score or standard Gaussian transform of the data distributions. Okay, by theory, they should be Gaussian because the simulation occurs in a Gaussian space. Okay, after a transformation of the data to Gaussian. Okay, and we'll get more into that when we talk about simulation later. The second thing is when you go to Gaussian, it does help you a bit with the cleaning up of the data. If you've got a little bit of outliers, if you've got kind of a real multimodal behavior and so forth, it's not a bad idea to clean up the data. Now, if you have really we're skipping a lot of data prep here. So if you really do have multimodal and in the data, you might want to look at separating it. And we do that here. We separate by facies. sand and shale because of that. But we're not going to cover a lot of that right now. Let's just take it as we'll do a Gaussian transformation, specifically because we want to use these variograms in the future in simulation, which is commonly what goes on. Now in GeostatsPy, we put in a Gaussian transformation. I have to admit, I actually like this transformation more than the other kind of popular transformations I found. I found there's some issues with spikes they're creating, with assumptions of the tails of the distribution and so forth. I find this one works pretty well. And all I did was take the GeostatsLib implementation of it. Okay, so with any command in Python, you can just say the name of the command. It'll tell you what are the parameters that you're going to need. Now, of course, you could also put a bracket here, do a shift tab, and you get access to the doc strings. And so you can actually look at that and go through here. And with GeostatsPy, we did an okay job. We wrote the doc strings. You can see what all the parameters are, and they're explained to some reasonable level. We'll make improvements in the future. Okay, so we got to populate with these parameters. We need the data frame. We need to know the variable that we want to transform. And we could use weighting if we're using declustering. We won't do that right here. We'll keep it simple. For variogram calculation, the use of declustering has been introduced in the past couple of years by the consortium up in Alberta. In general, before that, there was not declustering in variograms. I don't think it's really, I don't argue against it, but I don't think it's the common practice. And in the course, I tend to teach common practice. I don't tend to teach kind of more the research side of things, okay? And so also have the opportunity to provide a reference distribution to assist with the transformation. So in other words, we're doing the quantile transformation with the reference distribution to get that rather than the actual data to build that transformation, right? And then we just apply the data to the transformation. In this case, we're just going to use the data. We're going to keep it really simple. So if you look right here, all I'm doing is I'm going to transform porosity, permeability, all facies, sand, shale, all facies, sand, shale. And the result is I'm going to get brand new properties in my data frame. So I'm going to have a feature for normal score transformer, or NPOR, for the all facies, sand, shale, all normal score transformer permeability for all facies, sand, and shale. Okay, so we'll accomplish all that with that block of code. Now we can just do a quick preview, make sure we got what we expected to get, and look at it. We've got a normal score transformer, porosity, permeability, and this is the case of sand. So this will be a normal score transform, mean of 0, variance of 1 for all porosities and permeabilities, sand. Now, of course, we could always just very quickly just do a little check here and confirm that we also have that column, those two new columns appended now for shale. And if we go like this, we can now look at all faces together, and we'll see we've also done a good job. So we got the normal score transform, standard Gaussian transform for all of those cases, porosity and permeability. So it looks good. We're in good shape. If we want to say it looks good, we got to actually plot a distribution. That's the best way to really look at it. So let's just take a look at porosity, sand, and shale. Here's the original porosity, sand, and shale. As we mentioned, there's some overlap between the two. Shale is in blue, and you can see the sand is in pink. Purple is where they overlap together. And after transformation, look at what we got. We have pretty nice looking Gaussian distributions, not a huge number of samples, so a little bit of noise. We'd have a smoother looking distribution if we had many more samples. Okay, so we've done that. Now let's go ahead and look at the features. Now this is critical because anytime you're doing variogram transformation, you should look spatially at the features that you're working with. Make sure that there's nothing unusual going on. This is part of the data check, right? Like, is there something weird about the way the data is sampled? Are there clear spatial outliers where there's unusual samples that maybe we should look at? You would not detect them all the time on the histogram if they're locally or spatially anomalous, but they're within the distribution globally, right? Okay, so all facies, sand, shale. So you can clearly see that we have sand fairways and then shale in between. That's all good. We can look at the distributions. Now, if you look at the properties, notice that they're transformed between about -3 and +3, standard Gaussian transformation. So for sand, you'll range between there and the higher values. The higher values are more in this sampled pad here. And then you can see for shale, we also span between -3 and +3, and then over all facies taken together. Okay, so we're going to use that. Another thing we want to do if we're looking at the data is we want to get a sense of what's the data spacing. Because we've got to make a choice about the lag distance, the unit lag distance we're going to use here, right? Now, the extent of the data is 1,000 meters. We're going to probably want to calculate a variogram up to at least 500, about half the extent of the data. Of course, you could think, well, in 45 degree, you could go further, and that's fine. Maybe we'd go more on a distance of about 700 meters or something. That's fine. That's fine. The main thing is we got to recognize if you go 1,000 meters in the x direction, it would be very unreliable. We'd only be comparing pairs from here to here, very few pairs, and really only capturing the edges of the data set. Okay, so we look at it, we see the extent is about 1,000 meters by 1,000 meters. We can probably work safely up to about 500 meters. What's the lag distance? Well, the nominal spacing of the data, clearly there's kind of this regular spacing of the data at about maybe 100 meters. It looks like it's about 100 meters, right? From here to here, 200 to 300 in the x direction. So about 100 meter spacing. We've got a bunch of data that's kind of closer. And then we got these pads, these kind of local study areas with very dense data. Okay, so this will be useful to us. We can determine the lags that we should work with. Okay, so now let's go ahead and we're going to work with Gamby. We got Gaussian transform data. We visualized it in space, and we're ready to go ahead and do some variogram calculations. Now, we got to work with some parameters here for Gamby, and specifically, we're going to have parameters like the lag distance, the lag tolerance, the number of lags, the bandwidths, the azimuth, the tolerance, and whether or not we standardize the feature. Okay, let me explain each one of them, and they're listed here. We have trimming min and max. This is in case you had data for which you assume that some values are kind of non-physical, you need to remove them, and so you'd use trimming limits min and max to say, well, I don't want to take values that are too high or too low. We'll set them as -999 and +9999. I should put 4 nines there, sorry. Because we're basically saying no trimming. Just take all of the data, we're comfortable with it. Then the lag distance. Well, you remember we looked at the data spatially and we saw a spacing, nominal spacing where we think we get reasonable number of pairs would be about 100 meters. Now you could look at this pad here and go like, whoa, but that's very close. Like that's maybe more like 30 meter spacing or something like that. But what I would argue is that you only have that at a very specific location in the reservoir. I wouldn't want a whole bunch of short scale information about spatial continuity coming from just one specific location. I think we do better if we use a lag distance that's more general to the entire area of interest. Now, I wouldn't argue if one wanted to do that as part of your regular study to try to explore and understand, but we would do that under the consideration of it's just a small subset for which we have that information. I don't want to do that right now. For someone who's calculating their first variogram, let's just keep this simple. Okay, so lag distance of 100. As we discussed before with the parameters for tolerances, well, start with the lag tolerance of about 1/2 the lag distance. That way in the search template, there's no gaps, there's no overlap, it's simple. Now, as I mentioned before, we can probably go about 500 meters, but we could go 700 meters if you're 45 degrees, because your extent, about 1/2 would be about 700 meters. That's okay. So 7 lags of 100. We're now calculating a variogram for the bins. H, or lag offset, equals 100, 200, 300, all the way up to 700. Bandwidth. Well, let me first go to the azimuth tolerance. We're going to pick an azimuth tolerance for this variogram, this first variogram, as just being 90. What 90 means is I'm going a direction plus or minus 90 degrees. That's effectively an isotropic calculation. It's not going to be sensitive to direction. Therefore, the azimuth can be set to anything, and the bandwidth should really be set to a very large number, because that bandwidth would be an artificial truncation in one direction, which wouldn't make any sense because we're really trying to be isotropic. We really don't care about direction. Just make it big, get the bandwidth out of the way. Okay, and ISIL, from the GeostatsPy program, it's just whether or not you want to standardize the feature before variogram calculation to enforce a SIL equal to 1. Not a problem for us. We already Gaussian transform, standard Gaussian transform. So we have a mean of 0, variance of 1. We don't need to do that. We're good. Okay, so let's go ahead. We can run the variogram. Now, if you look at this code, it's just setting the parameters as we just talked about. You notice how in the box there, in Markdown, you can make it look like Python. Check out the Markdown there. It's really convenient for documentation. But then once we've established those parameters, we can go ahead and run the variogram for sand, shale, and all facies mixed together, porosity, and permeability here. So we're going to run all the variograms in one fell swoop, and then we can go ahead and do some changes, make some choices, right? Okay, so when we run that, the output is going to be a one-dimensional array, lag, which is just going to be the lag bins so you can plot the variogram. So we did lag distance of 100 meters, 7 of those. So now what's going to happen is we're going to end up with that array is going to be 100, 200, 300 through 700. So we can plot it. Then the next part is going to be the variogram value for those bins. So the first one's going to be 100 through 700. The next one's going to be the variogram value for each one of those bins. So we can plot them against each other. And the final one here is going to be the number of pairs used in the calculation, which is great to visualize and look at to get a sense of the reliability of the calculation. Now the rest of this code is just plotting. Not a big deal. We're going to plot sand, porosity and permeability on 2 separate plots, isotropic, and we'll do it by facies and all taken together. And there we go. That's it. Okay, so let's focus on the black X's here because they're all facies taken together. Okay, so we go from here, 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 and above the sill for this one right here. Okay, so we've calculated all of these values. Now, what you'll notice is that this has a very nice behavior. It's monotonically increasing. I would suspect that there might be some type of trend features. I'm probably getting ahead of myself right now because this is a lecture just on raw calculation. I can't help myself. I want to interpret variograms every time I see them. We'll do that in the next lecture. We'll spend more time on that. Okay, now the yellow are the experimental variograms for sand only. And the shale is the case of porosity, normal score transformed for the shale. And so what's fascinating is what we have here is we have pretty good continuity all taken together. The sand does okay, and the shale actually has pretty poor continuity. You might suspect a lot of low, or I should say short scale discontinuity, or maybe even nugget effect. This might be a good time to investigate looking at smaller bins and looking at the data study area with the closer spaced data to establish if there's nugget effect or not in this data set. All right, so now we've done a very basic variogram calculation. What can we do to experiment with this? And it's really easy to experiment now because we in fact have all of the parameters right here. So lag distance, we could change that to 50, half the lag distance, and see if we can do anything with that. The lag tolerance, we could set that to 50 also to give it a little bit of overlap and a little bit of smoothing to keep it really, really well behaved. Or we could go to 1/2 the lag distance, like I indicated in the documentation above. I just realized I used 100 and 100 before. That's fine. I just had some overlap between the bins to smooth out the results a bit. So I'll keep it as 50 and 50. And now to get to 700, now I've got to work with more like 14 of these bins. Okay, we'll stay isotropic and we'll just repeat the calculation. Look at that. Whoa, that's better. I think that's better. Now we're seeing a lot more detail. Remember, the choice of the lag distance and the lag tolerance is really a choice around this whole binning, just like the issues around histograms and binning of histograms. If you used too small of a bin, you get too much noise, too few samples per bin. And if you use too big of a bin, you get too much smoothing, you lose information. Now I'm feeling pretty courageous now. So I'm thinking, why don't we go ahead and try dropping the lag tolerance to 1/2 the lag distance and see if we get even more information, less smoothing, right? Okay, let's go ahead and run that. That's not bad. That's actually not bad at all. It's a little bit more noisy. We could probably up that again a bit because we do have some points where you see jumping up, coming back down for the sand permeability result. But in general, not too bad. The other thing, notice since that we've gone to a smaller bin size, we've resolved the short scale much better. And now we can see that probably not nugget effect. Maybe we have two different structures, but once again, I'm getting into interpretation. Okay, now we've accomplished that. I want to go ahead, I'll do one more thing. What I'll do is, let's remove all of the other variograms. We're just going to do the porosity, all faces together, and we'll run that, and we'll just take a look at that. So this is all faces together. And let's go ahead and try something out. Let's change the direction. Let's try a different direction. Now, if we go back to the data and we look at the data, porosity, all faces together, kind of hard to visualize, kind of hard to figure it out. Maybe there's a primary direction in the Y, in the zero azimuth, and a major direction in the Y and a minor in the X. Why don't we check? Okay, so what we'll do is we'll go ahead and set the azimuth to 0, that's good. But the azimuth tolerance, let's decrease it to 22 or something like that, or 20 degrees, that's fine. And let's go ahead and calculate that. Now, what we've done, now let's pay attention to that. So if we go ahead and we were to fit a variogram through that, we'd see a range of about 450 or so meters. That might be pretty reasonable. Let's go ahead and change this now to an azimuth of 90 and rerun that. Oh, and now a range of more like 550 or 600 meters. So my intuition from just looking at ocular inspection on that plot of data, I didn't have much certainty, but was somewhat reversed. It looks like we have a stronger degree of spatial continuity. In other words, longer range in the X direction than the Y direction, and an anisotropy basically going from 600 to maybe about 450 or so, 500 meters in the other direction. So we have something going on here with directionality that we could explore and calculate directional variograms. Now, 2 is not enough. We'd probably want to look at multiple variograms. I have another workflow where I calculate a whole bunch of different variogram directions, and I also do variogram maps for detection of directionality in a spatial phenomenon. But I just want to demonstrate right now just calculating some directional variograms. You could easily add that into this workflow. All right, so that's it. I hope that was useful to you. I'm Michael Pyrcz. I'm an associate professor at the University of Texas at Austin, and I record all my lectures on data analytics, geostatistics, and machine learning. And I do that to support my students and, in addition, working professionals who are interested to learn new skills to address the digital transformation that we're all facing right now. I'm always happy to discuss. You can reach me. I'm available on Twitter. I'm the Geostats guy. GitHub. I have repositories with lots of resources to share. I have a YouTube channel, and I'm super easy to track down at the University of Texas at Austin. So I hope that was helpful to everybody. Take care.